All right, now let's talk about phase. And not to disappoint you, but it's not like phasers, but it's just phase. 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 I'm going to move over, since everybody wrote phase, and I'm going to move over here, and everybody goes, wait, I didn't write phase. Just write 4 and then phase, okay? Phase. Phase is, I'll rewrite it, phase. Phase. It is the angular difference, between 2 points on an AC waveform. 2 points on an AC waveform. Well, we just looked at that a little bit. We had 0, then 90, then 180. You guys remember that? Because it was before break. I don't know what you do outside on break.
Well.
It's all right?
Yeah, I remember.
Okay, good. Somebody does. So that was the angular difference. It's in degrees. There's one way of looking at it. So one thing that we can look at here is in phases, we can have polyphase. Poly from the word meaning many phases. And we talked about this a little bit ago about 3 phase. So some AC circuits use multiple phases. Phases, like 3 phase, which is kind of a common thing. Like 3 phase. Houses, typical homes don't have 3 phase coming in. They don't have single phase. But shops, my shop, we had to have 3 phase run in. We had equipment that ran off 3 phase. And the reason why you would want 3 phase is because you can have smaller motors that produce more power, and that's why they produce some equipment. So 3 phase, if you have 3 phase, we'll do that. So 3 phase. 3 phase is AC. That is 120 degrees apart on peaks, or apart on anything really, which is not easy to draw, but I will do my best here. So we'll use different colors. We'll use red. So if we had 1 phase, this is going to be hard. Then we added another phase. It would be, see, this is 0. This is 90. This is 180. So it is 120 degrees out. So we would look at well, 120 bit right there. Right? So we could draw it. Oops, we run it on the peak from 0. So 0, that, and we do another one. We'll do it in green. So that's out another 120 degrees. So it looks like that. So not too bad. I'd actually curve around, wrong color. But so you see each one of these is 120 degrees apart, or each one of these is 120 degrees apart. And so what you get, instead of looking, so look at the red, and you can see you had a peak right here, and then you don't have a peak all the way until over here, how far those apart. Right. So now you can have a peak, a peak, a peak, a peak, and so you have all of these peak pulses coming through, and so if you average them out, you have a lot more electricity, if you will, than you otherwise would have. So we can talk about that way. Just understand that's what 3 phase is. We're going to be spending a lot of time talking about volt-amp phases. So voltage / amp phase, or phase shift, if you will. So when I draw the sinusoidal waveform here, whether single phase or polyphase, I could be talking about volts. right? Like so the voltage increases in amplitude and changes directions, and it goes the other way. All right. So I could be referencing this as voltage. Like I say, well, that's a picture of the voltage, what it does. It goes up, it goes down. Well, guess what the amperage does? That. Or I could just say, nope, that's my amperage, right? But you guys know that voltage is usually more than amperage. So I could say this is the voltage, and then the amperage would look pretty much like this. It's just not going to be as much as what we had before. So in this case, I'm looking at it, I'm saying, well, it's kind of lockstep. It hits 0, it hits 0, it hits 0, and it peaks at the same time, and it peaks at the same time. And that would be something that is in phase. The volts and amps are in phase. But you can really actually get something that is like this. So if I said this is volts, because it's already there and that's the color I'm using, and this is amps, I could get something that was out of phase. Where the peak is here and this is over here, and it's like, what the hell did I just draw? It's like nothing really lines up. You know, this peak is just off from the 0 point. That's way out of phase. They're happening at different times. Well, if I drew it really nice, I could have drew the peak right over this. If I could have said the peak is right here and the 0 is right here, then it would be 90 degrees out of phase, where the volts is peaking out and the amps are building up. So it's kind of a hard concept to understand, because you don't think of electricity as doing that because of this time thing, but now we have to really think about it, and that's really what it does. The volts are doing one thing and the amps are doing something completely different. And when that happens and it's out of phase, it becomes an inefficient circuit. You start dropping off power. So just like before we said power is just amps times watts, well, it's going to change now. It's still the same concept of power, but we're going to be looking at power factors and how we calculate it. And that's going to include the frequency, and we're ultimately going to get down and say, is the circuit in phase with each other? And that'll be done by a power factor. So that's exactly what happens when it's out of phase. Let me see, AC circuits.
What was the word you used? Insufficient circuit?
Inefficient. Not efficient.
Not efficient.
It's inefficient. All right, so in AC circuits, it's possible for the peak voltage to happen at a different time than peak amperage. So, 1. In AC circuits, it is possible, not desirable, for the peak voltage to happen at a different time, than peak amps. If that is the case, then this is an out of phase. This is an out of phase circuit. And when we talk about out of phase circuits, this is going to become one of those Ohm's law things that you have to commit to memory, but it's not as hard as Ohm's law. It is called Eli the Iceman. Eli the ICE man. Eli the Iceman. And Eli the Iceman goes like this. If you can remember Eli the Iceman, first we'll talk about Eli. So E-L-I, Eli the Iceman. Inductance, which is coils. So if we have a bunch of coils in a circuit, then we're going to have inductance. And if we have inductance, coils, is represented by the letter L, by L. So that's why we have Eli. Got the L in the middle? That's Eli, L. So in an inductive circuit, voltage E leads current I. And we'll talk about the Iceman. Ice. So in a capacitive circuit, oops, I'll do it the same. Capacitance. Capacitance. Capacitors. Capacitors. It's empty. Tell me it's empty. Go get another bottle.
It's empty.
It's still dripping out.
It's empty.
Stop it.
Just run the pump up.
Capacitors, or capacitors is represented by C. So it is to say that in a capacitive circuit, I, which is current, leads voltage E. A circuit that is out of phase is, well, out of phase as far as volts and amps go. Volts and amps. Circuit that is out of phase in volts and amps is less efficient.
Is either one of those Eli or Ice out of phase?
They're both out of phase.
Got it.
Eli represent. So back up a little bit. So Eli, L, inductors. Inductors are this interactive coils. So if I have a circuit, and really we're just talking about circuits that you're just looking at, they just look slightly different now. So now I'm going to have an AC waveform, an AC generator. There it is, instead of a battery. So I got something like that. And then I go up, and then I'm going to put, what is that? That's an inductor. That's a coil. And then I come around, and I can do something like that. That is a capacitor, right? And then I have a resistor. What is that? Resistor. It's a load. And we're going to be evaluating these circuits. And at some point, not right now, but we'll talk about how big this coil is versus how big the capacitor is versus how big the load is. Okay? And so if the coil, we're just going to use big right now, but if the coil is bigger or more powerful than the capacitor is, and that's a mathematical formula to do because they're measured in different scales, henries versus farads. So we have more henries than we do the farads, more coil than we do capacitor. Then we're going to look at Eli, and we're going to say what happens?
Voltage leads current.
So the voltage is going to go first, and then the current's going to start. Remember, voltage is the pressure, and current is the actual movement of the electrons.
Mm-hmm.
All right? So if we turn it around, we say, okay, now the capacitor is really big, and we have very small coil, then the current is going to go, and then the voltage is going to happen after it. So one leads and one lags. Now, the reason why this is because in a coil, in an inductor, just like it's drawn, it's just a loop of wire. So there you go. There's a coil right there. So if I were to take an ohm meter and check the resistance of this wire, what do you expect I would see?
Hopefully Zero.
It's just wire. So don't be afraid.
No resistance.
Be none. Be no resistance. So, because it's not. There's no resistance. It's just a wire, a straight wire. I don't have any wires in here. It's just a wire that's curled up. So if it's a straight wire, how much resistance do you usually have in straight wire? Zero. So now I just curl it around my pencil. How much resistance? Does it change?
No.
Okay, so it doesn't change. But what happens very quickly with DC, believe it or not, but we never talked about it, is when you close the switch and the current starts to flow through a coil, it builds up a voltage inside of it. And that voltage, and we're going to write about this, and I'll give you notes, but that voltage builds up. And so we have voltage, not voltage, we have voltage goes through it. You have voltage through a wire. Voltage through a wire creates, anybody remember? Electromagnetic force. So we have a magnetic field grows around the wire. If a magnetic field is growing, then the magnetic field is moving. If the magnetic field is moving relative to a wire, what do we create? Voltage. So sometimes the magnets move and the wire stays put. Sometimes the wire, the other way around. So in this case, the wire doesn't move, but the magnetic lines move. So that because that's the whole key to this. When magnetic lines grow out, the magnet moved. When you take away the magnet, they move this way. Magnetic lines moving back and forth across a wire create voltage. Okay, so when you have a DC circuit and you close the switch, so all that voltage goes running through that coil, it creates its own voltage, which goes the backwards way. So voltage comes running in, creates voltage within the wire that wants to go that way. So you have voltage from the battery coming this way, but voltage from the wire going that way. That's called resistance. But with your DC battery, when you close the switch, it builds up and then it stays. So that is not movement. It's static. So it goes away. So the current just flows, and you never know the difference. Then you open up the switch, and the magnetic field in the coil goes the other way. So now the voltage goes, well, okay, we're leaving now. We're done. But the coil says, no, you're not. It builds up and goes that way, and it stops the voltage from wanting to back off. So in a DC circuit, that happens twice. Once when you turn it on, once when you turn it off. Now an AC circuit is going back and forth and back and forth. So right here comes the voltage going this way, builds up across the coil. The coil says, no, everybody wait. Right? So current, it's telling the current to stop. Current, you got to stop. The voltage built up. That's why at Eli, voltage went, built up, then turns around and says, current has to stop because it built up. Right? Then it gets to a peak and then it kind of lets it start to go. Then it turns around and then the field starts to collapse and it turns around and goes, all right, all the electrons got to stop this way. Well, they don't necessarily stop, but it sure is a lot of resistance and it really slows them down going this way. And so that's why voltage goes and then the current goes. Current's always late to the party because the voltage is always trying to hold it up. Now check your ID, please. It's sitting at the door, won't let it through. So there we go. So voltage is building up. It has no problem. It gets there first, so it causes the problem, and then the current can't get through. Everybody's with me on that one? Okay, hopefully that kind of explained it.
Can you scroll back up?
All right, so why is it the opposite with capacitors? Well, a capacitor, I'm going to scroll down for a minute. I'll go back. I'll give you time. A capacitor, as you can see schematically, is two plates, and that's really all it is. It's a giant, you can picture it as huge plates of steel if you want. They don't touch. But they're not steel, they're just pieces of conductor, metal, foil, something that is very close together but doesn't touch. So if you have a DC circuit, your battery, and you take two wires and you bring them almost to touching but don't touch, what do you have? You have an open circuit. Two wires that don't touch is an open circuit in DC. You turn the switch on, what happens? Nothing. Okay, but now if you connected it to two very large plates that were just, I mean, a piece of paper apart, well, what happens is when you turn on the battery with DC, it will initially allow electrons go until they fill up the plate, and then it just stops and goes, well, you know, what are we doing? There's nowhere to go. We're done. Okay, so but in AC, you have these plates and you turn it on, and all the electrons go, it's wide open, it's a superhighway, and so there's no resistance whatsoever in a capacitor. So all the electrons take off running with no voltage whatsoever, because it doesn't take any voltage, because they see this. It's like the kids at freaking Marine World, or not Marine World, it's Six Flags, man. You get to the gate, boom, they're off, you know. So electrons are off to the what do you call it, amusement park, right? And here's the parents, the voltage, you know, dragging along. Not getting on that debt trap. So, all right, then the voltage starts to build up because it took time for the voltage. But the electrons were free to run because they had zero, absolutely no resistance whatsoever, and they start filling up that plate. All right, and then here comes the voltage builds up. Okay, by the time the voltage builds up and starts to fall back off and start to go the other way, all the electrons are going, dead end, the other plate's the way to go. So they go running by and they go fill up the other plate, and then the voltage kind of gets to the bottom, and then it turns around, starts going the other way. Well, now the electrons already filled up the other plate. So you see the electrons, the current is always leading the voltage, who is just on, you know, it's on a timer. So
they don't cross that plate, they just go back.
They can't. The plates don't touch.
Okay.
So they're always going back and forth. Well, again, I'll tell you this, which is going to come up later, but in a DC circuit, we've said that's an open, but in an AC circuit, it's not an open because of the way the current's always going back and forth. Kind of, if you will, the plate fills up this way, then it just fills up the other way, then it fills up this way, so it's allowed to go back and forth. It's simplifying it, but it does. In an AC circuit, it's not an open. Yeah.
Just to make sure that my head is following you here. So you're saying that with that small gap in between, the idea is not an arc. It's not to jump across.
If it did, you've got a blowout.
Right. We have two very highly charged plates.
Yes.
Is the idea to then tap into those plates and alternate polarity so that we're able to pull from that? Or what,
No.
what's the whole purpose of the capacitor?
Okay, and again, we're a little ahead of ourselves, but a capacitor, it's two things. One, we're talking about out-of-phase circuits.
Yep.
So if Eli makes the voltage lead and the current fall behind, and a capacitor does the complete opposite, when you mix them and get them in balance, then you get a in-sync waveform.
Okay.
So quite literally, if you had a bunch of coils, you would just add capacitors to bring it back into phase. And you'd say, well, the capacitor's only there to do it in phase. When we talk about magnetos, we're going to show how a capacitor or a condenser, its name changes, it's the same part, it tricks electrons. When you open the breaker points, like in an old style ignition systems, as you're opening up the breaker points, the electrons will jump across it because it's like, hey, everybody, this is the way to go. But at a capacitor, an electron's like, I'm not jumping that. There's a shortcut. Follow me, everybody. And they all go running around to the capacitor like a bunch of idiots. By the time the capacitor fills up and they realize that the capacitor is a dead end and they should have went through the points, and they all turn around and go run through the points are already too far. They can't make the jump. So it keeps the points from burning and arcing. We'll cover that again in 2 weeks. So, but for now, the capacitor balances out the inductors. Or if you had a bunch of capacitors, don't know why you would, then the inductors would balance those out. So you build a circuit. So most circuits, if you think about, lights and motors and things that have coils in them, that does the work. You'd bring capacitors in just to make sure it's in phase. Like I had mentioned, my father-in-law worked for SMUD, and so everybody turns on their air conditioner. Those are all motors, And they're over at SMUD going, man, we are getting out of phase. They just have huge capacitors. They just bring it online. Boom, bring on the capacitor. And that starts to shift the phase back into where they're both doing the same thing. And that's what we want.
Is a capacitor and a condenser the same thing?
Same thing. Right, and you go back up. Everybody's good here? All right, let's see, point D. Here we go, D. D, phase is represented in degrees. Phase is represented in degrees. Degrees called phase angle. All right, effective power. When measuring DC, direct current, the effective power is the same as measured values, is the same as measured values. So effective power is just whatever you measure, and you come up with power, which is volts times amps, and you get your power. There you go, you're done. Because everything you measure is what you measure. Not so much with AC. So in AC, the maximum measured value only happens twice per cycle. So in AC, the max measured value only happens twice per second. Only happens, not twice, twice per cycle. So during this period of time, our house outlet, 1/60th of a second, for every 1/60th of a second, you have a peak, and all the rest of the time in between, it's less than peak, and sometimes it's zero. So the actual power you're getting is not what we measure. So therefore, an average value must be used. And somebody else figured, I'm going to write this, note that the plus and minus values do not cancel each other out. So otherwise it'd be zero. If you added all the positives, like figured, 50 spots on the up arc and then 50 spots on the bottom arc, and you added them both together, you would get zero because they cancel each other out, but it doesn't work that way. You actually use, yeah.
I'm sorry. But we only have three phases. We get a negative swing and a positive swing.
Even in single phase, you get a negative positive swing.
I mean, they're happening at the same time on the graph.
They're in separate wires.
They are in separate wires.
Okay.
The effective. So somebody figured out this. You would think they would have just done it mathematically first, or they did it mathematically and then did it this way and said, yeah, that works out. But I like this because it just kind of makes sense to me. The effective value of AC is that which produces the same heat value in DC, the same heat value. So I kind of picture it like this. you have a student who is doing some work with a circuit and they overdo it and those resistors get really hot. Or they do it right, just like you do in the ni-cad with 6 amps, that resistor gets pretty hot, right? Okay, so they figured out that exact value with that amperage and that voltage and come up with the power. Okay, so you have, 1.2 volts and 6 amps, and so you roughly have, 6 watts of power through there. So they take it apart and then they get an AC generator and they have to turn up the AC until they get the same heat. Okay, measures the same now. And so like, what do you got over on the scope? And like, wow, we're doing a lot more than 1.2 volts. We're up at, 1.4 times that. So like, okay, well, there we go. That's the same then. So that power is that power. Or you did the little motor project and you made a lot of smoke. It's how much AC would it take to make the same amount of smoke?
Say that again?
The smoke part? No, I'm not going to say that.
Next project.
What's that?
I said I need that for my next project.
Yeah. All right. Did you want me to say something again?
No.
Okay, you're just messing with me a little bit. All right, so 0.3, I don't know where I'm at here. The formula for power. Formula for power. This is going to blow your mind. P equals I times E. Or if we look at the whole Ohm's wheel, I squared R, or, let's make it or, E squared divided by R. So I'm not going to write all this because it kind of got out of hand here. So to figure out the average AC power, so like I said, so now we're looking back at AC power and say, okay, well, what is the average of all of those spots then? If we just put a dot every, so many fractions of a second, and we said, okay, let's add them all up and then average them, it would obviously equal 0 because you have positives and negatives. So the way they did that is they squared all the values. Now they're all positive. And then you take the average of the square root of those, thus being the term root mean squared. So the root of the average mean squared. So root mean squared. So we're looking at root mean squared. Will give you the effective voltage. So the root mean square value is the effective voltage. And that's what I'm going to go with. So just cut out a lot of stuff. So the effective is that one all right? Yeah. We'll say effective voltage. Yeah, I'll work with that. Effective voltage is called the root mean square. Root mean square, or RMS value. And of course, we're not going to thankfully have to measure all of those and then figure it out. They tell us a formula. So the formulas are easy. So E is what? So you guys know this. Don't be freaking out on me. So E effective is equal to 0.707 times E max. So if I said on an oscilloscope, because this is how I'd have to do it, I would look at the sine wave and I would measure the peak and I'd say, wow, the peak is 100 volts. So what's my E effective? I made it an easy number for you.
70.7.
70.7. So my E max was 100 volts. It's the peak of the sine wave. I multiply that times 0.707 and I get the effective. So it's the 706. It's just like 70 volts out of a battery, 0.7. All right. So E max equals 1.414 times, what the hell did I write here? Oh, what the hell? I went off of it. Oh, it's because I scrolled way the hell down. Okay, so E max is 0.1414 times E effective. Like, where the hell is it going with all this?
It's any easier, it's square root of 2, and the other one's 1 over square root of 2.
Not easier.
Not easier. Because it's the same number. Never mind.
All right. So if I said, hey, I plug in my voltmeter over here, and I said, wow, that's pretty weird, man. We had 110 volts coming out of there. And I tell you that is the effective. What would the max be?
More.
110 times 1.414. Okay, there we go. All right, I've just totally screwed up my notes. So now they're just like here. So I got to fill in for all practical applications. The value stated, unless otherwise noted or understood, is an RMS value. Unless otherwise noted. Otherwise noted or understood. So if you're completely lost, go RMS. Most instruments, that is VOMs, voltometers, multimeters, are reading or measuring, we'll say reading in RMS. That's why I made that example. I plug in the voltmeter, I'm going to get max or RMS or effective. I'm going to get RMS or effective. So yeah, household measures. Here's the funny thing. Sometimes we say 110, sometimes we say 120. I've even asked electricians, which one is it? I've even looked it up. Nobody has the answer. So if it's 120 out of the wall, it's what? If I measure it with my voltmeter, I get 120 out of the wall. That is considered peak or RMS? RMS. So if I want to know the peak, it's multiply. You guys should do this. Multiply it times 1.414. So I get
169.68.
169.68. Is that peak or peak to peak? It is in fact peak. So what is the peak to peak voltage then? Multiply it times 2, but that's really not something we work much with, but there it is. Okay.
Wow.
Oh, we're doing fantastic. So we covered a lot. Everybody keeping up with me?
So far.
Okay, we learned how we made AC. We've learned how that coils can be a problem. We're going to go over that again. We learned that capacitors can be a problem. We're going to go over that again. We've learned mostly here about peak. That's a big deal. Peak versus RMS and waveforms. Everybody with me now? All right. So don't be afraid to say, hey, can we go back over that again, because we're going to circle back around some stuff and make sure we understand. So if there's something that we get to and you're like, okay, wait a minute, now we're applying it. So I didn't understand it before because now we're applying it different. You just got to say, hey, Help me out here. Because really, this is not hard. So we're going to talk about it, but not you. AC, yeah, what?
I was going to say, the purpose of the RMS is to find the effective value, which would help us find the other current.
Okay, what you need to not worry about finding right now is you need to understand what it is you're reading and when you're reading it.
Okay.
So if you are working with AC and you take a voltmeter and you plug it in, and it's going to say 110 or 120. We'll say 110. And I should bring one in and measure it just so I'm just dead on. 115. So you measure it, but then you take an oscilloscope and you put it on there and go, well, dang it. How come the oscilloscope says 169 and my voltmeter says 120? Nah, I'm totally lost. Right? But are you lost?
No.
Hopefully not, because an oscilloscope is going to show you the true sine wave, which will show you the peaks. The meter can't do that because it's going back and forth. So because remember, a meter is literally a voltage device that's, it's current flow calibrated to read voltage. And so since the current is literally going back and forth, the needle's going to do kind of an average, which is 0.707. So if you have nearly 170 volts right there at a peak, your meter is going to average it and say it's about 110. Follow? Okay, so we gotta get that. So we're gonna walk slow here about an AC resistive circuit. So we're gonna talk about, when we talk about AC circuits, where we're going is RCL circuits. R being resistive, C capacitive, and L inductance. All right. So right now we're going to talk about an AC resistive circuit. So out of the RCL of them all, we're talking about the R part. So a resistive circuit. Now this is a circuit that only has resistors. So we call it a resistive circuit. And a purely resistive circuit. So this is a circuit that only, it's a circuit that contains only resistors. In other words, it's got no coils, no capacitors. If I mentioned Ohm's law is applicable just like DC. Everything's the same. Nothing else. I go on all day. Hopefully you get it. I've got this, why I thought about, let's do an example. No, let's not do an example because we've done 100 of them already. And when I say it's exactly like a DC circuit, I know this class knows what I'm talking about, and you know how to do a DC circuit. The only difference is going to be, instead of doing a battery, I'm not going to do a battery, get rid of the battery, and we change it, and we just put a circle with that. And that means AC. Otherwise, you would just do EIR, and you would go through, and you do, here's a resistor, and come back around. I have to go like that, because that's what my picture is, and say, okay, well, the EIR, Ohm's law, Kirchhoff's law, it's all the same, works just fine, nothing new, all done. So let me see. Where was I? Here's your peak, voltage. Where did I got the page 10? Got them out of order. There we go. 9, 10. All right. Circuit contains no resistors. Ohm's law is applicable. Example, I had 110 volts RMS AC power supplying 2 parallel resistors of 10 ohms each. It's all the same. When we get done. In a purely resistive circuit, volts and amps are in phase. Ohm's law is applicable just like DC. We'll make this point C then. In a purely resistive circuit, volts and amps are in phase. Which means when the voltage reverses, amps reverse. Same time, same moment. In every step in time, volts are doing the exact same things as amps, but at a different amplitude. Because volts are up here and amps are down here. All right, so if I had 110 volts and 5 amps, well, of course, volts are up here and amps are way down here. But they're going to peak together and they're going to come down and hit 0 together. And then they're going to go down and peak together, but not quite as much. And come up and find 0. They'll meet up at 0. Catch you later. You go to peak. I'm going to go to my little valley, my little mountain. You go up to your big mountain. Come back. I'll meet you back at 0. And they go back to 0. Got it? Because that was an easy one, right? Volts, amps are in phase. Power consumed is the same. Is same as DC, is the same as DC. So we can go power equals E RMS times I RMS. We could do the same. We'll just go with that. All right, that's a good place to stop.